Sensors. Article. An energy balance clustering routing protocol for intra-body wireless nanosensor networks. Wan Shu *, Yan Zhang, Zhaolong Zhang and Jiali Khan. School of Electronics and Information, Tongji University, Shanghai 201804, China. Received, the 9th of October 2019, accepted, the 5th of November 2019, published, the 8th of November 2019. Abstract. Wireless nanosensor networks (WNSNs) are a new type of network that combines nanotechnology and sensor networks. Because WNSNs have great application prospects in intra-body health monitoring, biomedicine and damage detection, intra-body wireless nanosensor networks (IWNSNs) have become a new research hotspot. An energy balance clustering routing protocol (EBCR) is proposed for the intra-body nanosensor nodes with low computing and processing capabilities, short communication range and limited energy storage. The protocol reduces the communication load of nano nodes by adopting a new hierarchical clustering method. The nano nodes in the cluster can transmit data directly to the cluster head nodes by one hop, and the cluster head nodes can transmit data to the nano control node by multi-hop routing among themselves. Furthermore, there is a trade-off between distance and channel capacity when choosing the next hop node in order to reduce energy consumption while ensuring successful data packet transmission. The simulation results show that the protocol has great advantages in balancing energy consumption, prolonging network lifetime and ensuring data packet transmission success rate. It can be seen that EBCR protocol can be used as an effective routing scheme for IWNSNs. Keywords: intra-body wireless nanosensor networks, terahertz communication, clustering. Routing protocol. 1. Introduction. Nanotechnology plays an increasingly important role in many fields such as environment, industry, biomedicine and military with its rapid development. Subsequently, the concepts of nanocommunication and wireless nanosensor networks (WNSNs) were proposed. 1. Nano devices can communicate cooperatively and share the perceived information. Due to the significant advantages in size, biocompatibility and biostability of nano devices, WNSNs have great application prospects in intra-body health monitoring and medical treatment. Thus, intra-body wireless nanosensor networks (IWNSNs) have also become a new research hotspot. The development of new materials such as graphene-2 and carbon nanotubes (CNT3) that can work at terahertz frequencies 0.1-10 terahertz opens new opportunities for applying these nano devices to the body. This underutilized terahertz spectrum 4 to 7 will have a major impact on future medical technologies. First, it can provide a wide bandwidth and the antenna size can be made small. Second, it is less sensitive to propagation effects such as scattering and it is relatively safe for biological tissues. 8, 9. Therefore, terahertz wireless communication is an ideal choice for IWNSN physical layer technology. As one of the key technologies of WNSNs, routing protocols have been studied by scholars in recent years. Currently, researchers mainly study three types of protocols: FL-routing protocols, proximity routing protocols and energy harvesting-based routing protocols. 2 of 23. The FL-routing protocol is very simple, which is consistent with the characteristics of limited nano-node energy and computational power 10. However, FL-routing protocols can cause broadcast storms and excessive retransmissions, thereby increasing energy consumption. Proximity routing protocols attempt to improve the performance of FL-routing protocols by controlling the number of neighboring nodes. Examples of these protocols include Corona 11, SFR 12, and EEMR 13. Corona is a geographic FL-routing protocol that assumes that nodes in a nano network consist of two types: anchor nodes and user nodes. Anchor nodes have higher communication and processing capabilities than user nodes. User nodes need to localize their location relative to these anchor nodes. The scheme assumes a square FIXED network topology in which 4 anchor nodes are located at the vertices of the square network. A selective FL-routing routing (SFR) based on terahertz band communication is proposed in 12. In order to avoid waste of bandwidth resources caused by repeated forwarding of the same data packet, the protocol optimizes the FL-routing direction. The trend of forwarding packets to the destination node is guaranteed, thereby reducing the number of messages in the network. Shu et al. Proposed a protocol called EEMR13 to solve the problem that the routing protocols such as Corona and SFR do not consider the terahertz channel attenuation characteristics. However, the EEMR protocol is a single-path routing protocol, which has poor adaptability to network topology changes. For example, it cannot solve the problems that the nanonode's failures due to energy exhaustion or the temporary interruption of the transmission link caused by molecular group disturbance of the channel environment. Energy-based routing protocols 14 to 16 are specifically designed for self-powered nano networks. The main goal of these protocols is to balance energy harvesting and energy consumption, so that the lifetime of the network tends to infinity. In designing such routing protocols, the trade-off between the complexity and accuracy of the protocol should be considered. For example, Pierre Aubin et al. Proposed a routing framework based on energy harvesting 14. Because of the adoption of the energy harvesting mechanism, the consideration of the trade-off between energy harvesting and energy consumption, and the establishment of multi-hop routing based on the transmission characteristics of the terahertz channel, the routing protocol can maximize the throughput of the network while ensuring that the network lifetime is infinite. Using the energy harvesting mechanism to make the network lifetime infinite is a major innovation in this protocol. However, the protocol proposed in this paper is too complicated. In the simulation, the maximum number of hops is 2, which is not enough for the practical application of the routing in WNSNs. Morekish and Weigel take into account the current state of energy collected by the communication nodes, and proposed an energy model based on the Markov decision process for data propagation 1.5. However, due to the complexity of the proposed model, the authors adopted a lightweight heuristic scheme. Xu et al. Proposed a multipath routing protocol EHMR 16 based on energy harvesting. The protocol uses a piezoelectric energy harvesting system to break through the bottleneck of node energy and quantify the contribution of nodes joining paths through the game routing model and establishes multiple feasible paths to improve the stability of the transmission. However, in the route maintenance phase of the EHMR protocol, the forwarding failure is handled by switching the route, and the delay is exchanged for the transmission reliability, which is not applicable to the IWNSN with high delay requirement. At present, the research on routing protocols is still in infancy. Although 17 proposed a cluster-based network topology, the proposed routing proposal did not consider the characteristics of the intra-body nano network FIRSTLY, and secondly there was no reasonable cluster head node update mechanism. In addition, the author did not give a routing decision process for nodes between clusters. Therefore, we will study the routing protocol of IWNSNs in this paper that considers the special application environment in the human body. Due to the small size of the nanosensors, the calculation and processing capabilities of the nanonodes are limited, and the energy they store is also very limited. However, the nanosensor is very easy to deploy because of its small size. Usually, many nanonodes are deployed in the target area to ensure that enough data can be collected to complete the monitoring task. Due to the large scale, 3 of 23 of the network in the small communication range of the nanonodes, clustering is used to realize data transmission. In response to the above problems, we propose an energy balance clustering routing protocol EBCR. The protocol adopts a new layered clustering method to reduce the communication load of the nanonodes, and it also can reduce the number of member nodes in the cluster, and the data packet within the cluster can be transmitted to the cluster head in one hop. In addition, by continuously updating the cluster head node, the node with higher residual energy is selected as the cluster head, which prevents the cluster head node from exhausting energy due to frequent data forwarding, and can also balance the energy consumption in the network. Finally, the cluster head nodes transmit data to the nano control node through multi-hop routing. When selecting the next hop, the distance and the channel capacity is compromised to ensure that the data packet is successfully transmitted while reducing the energy consumption. The remainder of this paper is organized as follows. In Section 2, the system model is introduced. Next, the clustering routing framework is described in Section 3. In Section 4, we introduce the simulation scenario and define 4 evaluation indicators: average residual energy, number of dead nodes, data packet transmission success rate and control overhead to evaluate the performance of the new EBCR protocol. Following this, we demonstrate and analyze simulation results for the performance of EBCR protocol in Section 5. Finally, we conclude this paper in Section 6. 2. System model. The computational processing capacity of nanosensors is limited. Many nanonodes must communicate cooperatively to ensure the normal operation of wireless nanosensor networks. Therefore, IWNSN in our paper is designed as a layered clustering structure. The nanonodes are deployed in the target area to perceive the data in the environment. The small volume limits its storage and computing capacity, and can only communicate for short distances. Therefore, the nodes in the cluster can transmit data to the cluster head by one hop. Then, the cluster head nodes transfer data to the nanocontroller NC through multi-hop, which has larger volume and stronger calculation processing capability than the nanonode. The NC's main task is to control nanonodes by broadcasting simple commands, combine the collected data and ultimately forward it to the nano interface device. 2.1. Network Model. In the EBCR protocol, the network topology of IWNSNs can be represented as G equals V, E where V equals V1, V2, Vn represents a set of all nanonodes and nanocontrol nodes, and N equals V is the number of nodes. The proposed routing framework, shown in Figure 1, is a multi-layer topology based on the distance between nanonodes and nanocontrol nodes. In order to improve the stability of the network and achieve high-energy EFFIHNC, each layer is divided into multiple clusters to avoid repeated clustering. The cluster head node cluster header, CH, of each layer is selected based on the residual energy of the nanonodes. The cluster head collects data from the cluster member node, CM, and then forwards the summary data to the NC. The clusters of each layer can communicate with adjacent upper or lower clusters. The network model has the following assumptions. The positions of the nanonodes and the nanocontrol nodes are FIXED, and the energy of NC is not limited. The terahertz communication of the physical layer of IWNSNs uses TSOC modulation, which is like the impulse radio ultra-wideband IRUWB technology, which can accurately locate, and the nanonodes can obtain the location information of other nodes by broadcasting a simple message. In the process of perceiving, processing and transmitting data, the energy consumption of nanonodes is mainly concentrated in data transmission. The energy consumed by the nanonodes due to the perceiving and processing data is ignored in the energy consumption model. 4 of 23. Figure 1. Layered clustering structure of intra-body wireless nanosensor IWNSNs. 2.2. Intra-body terahertz channel model. The path loss of the terahertz channel consists of three parts. The loss experienced by the terahertz wave propagating in the medium, the loss caused by the molecular absorption and the scattering loss during signal propagation. 18. Therefore, the path loss can be expressed as PLF, D equals PL, F, D times PL, F, D times PL, F, D. 1. Where PLF, D is the total path loss, place. F, D place. F, D and PL, F, D represent the propagation loss, molecular absorption loss and scattering loss respectively. Propagation loss represents the transmission loss of electromagnetic waves in a physical medium and can be modeled by a path loss formula freeze, which is defined as PL, F, D equals 4 pi dn, lambda, 2, where D is the propagation distance, lambda, is the free space wavelength and n represents the refractive index of human tissue. At the frequency of 1 terahertz lambda equals 300 micrometers, the propagation loss is quite high, severely limiting the transmission range of the nanonode. Therefore, in the human body scenario, the communication distance between the nanonode and NC is drastically reduced. Molecular absorption loss refers to the attenuation caused by molecular absorption. Usually, when electromagnetic waves propagate through the material, a portion of the electromagnetic energy radiated by the nano antenna is converted to the internal kinetic energy of the molecule. This process depends on the operating frequency and the biological tissue considered. For example, the absorption loss caused by propagation in the skin or blood is different. Thus, the molecular absorption of each material can be characterized by an absorption loss factor alpha F, which varies with frequency. Therefore, given alpha F, the molecular absorption loss can be obtained by the following formula. PL, F, D equals E. 3. Figure 1. Layered clustering structure of intra-body wireless nanosensor IWNSNs. 2.2. Intra-body terahertz channel model. The path loss of the terahertz channel consists of three parts. The loss experienced by the terahertz wave propagating in the medium, the loss caused by the molecular absorption and the scattering loss during signal propagation. 18. Therefore, the path loss can be expressed as PLF, D equals PLSPRF, D times PLabs F, D times PLSCAF, D. 1. Where PLF, D is the total path loss, PLSPRF, D PLabs F, D and PLSCAF, D represent the propagation loss, molecular absorption loss and scattering loss respectively. Propagation loss represents the transmission loss of electromagnetic waves in a physical medium and can be modeled by a path loss formula freeze, which is defined as PLSPRF D equals 4 pi dnm lambda 0. 2, where d is the propagation distance, lambda 0 is the free space wavelength and dnm represents the refractive index of human tissue. At the frequency of 1 terahertz, lambda 0 equals 300 micrometers, the propagation loss is quite high, severely limiting the transmission range of the nanonode. Therefore, in the human body scenario, the communication distance between the nanonode and NC is drastically reduced. Molecular absorption loss refers to the attenuation caused by molecular absorption. Usually, when electromagnetic waves propagate through the material, a portion of the electromagnetic energy radiated by the nano antenna is converted to the internal kinetic energy of the molecule. This process depends on the operating frequency and the biological tissue considered. For example, the absorption loss caused by propagation in the skin or blood is different. Thus, the molecular absorption of each material. Sensors 2019, 4875. 5 of 23, can be characterized by an absorption loss factor alpha F which varies with frequency. Therefore, given alpha F, the molecular absorption loss can be obtained by the following formula. P labs F, D equals E alpha FD. 3. Human tissue is composed of different types of substances. The deflection of the beam caused by this microscopic inhomogeneity will cause scattering of particles and AFFECT the propagation of electromagnetic waves. The path loss due to scattering can be expressed as PLSCAF, D equals E micro D. 4. Where D is the propagation distance, and micro is the scattering loss factor. It can be seen from 19 that the scattering loss factor is too small compared to the molecular absorption loss factor, which is almost negligible. Therefore, the path loss can be expressed as PLF, D equals 4 pi dnm lambda 0, 2E alpha FD. 5. The phenomenon of molecular absorption from the medium not only AFFECTs the characteristic of the channel in terms of attenuation but also introduces noise. This is the main noise in the terahertz band. The power spectral density of molecular absorption noise can be expressed as NF, D equals KBT0, 1 minus E minus alpha FD. 6. Where KB represents the Boltzmann constant and T0 represents the reference temperature. According to Shannon theory, the channel capacity can be calculated by the following formula. C equals log 2, 1 plus Sn. 7. Where B represents the total bandwidth of the system and Sn represents the signal-to-noise ratio. However, the terahertz channel is frequency selective and the noise is non-white noise, so the entire bandwidth is divided into many narrow subbands. These subbands are very narrow, so the subband channels are non-selective and the noise therein is white noise. Therefore, the capacity of each subband within the available bandwidth will be calculated to obtain the total channel capacity, so the channel capacity can be written as 20. C equals X, I, increment F log 2, 1 plus S phi PL phi, D N phi, D. 8. Where S is the power spectral density of the transmitted signal and the ITH subband is centered around frequency phi, having width increment F. 2.3. Energy consumption model. The energy consumption mainly focuses on the energy consumed by the nanonodes to receive and transmit data. The energy consumption of the nanonodes in receiving and transmitting data in the TSOC-based terahertz channel can be expressed as 19. ETX n-bit equals omega n-bit EPTX. 9. ERX n-bit equals n-bit EPREX equals 110 n-bit EPTX. 10. 6 of 23. Where ETX n-bit and ERX n-bit represent the energy consumed by the nanonodes to transmit and receive the n-bit bits data packet respectively, and EPTX and EPTX represent the energy consumed to transmit and receive the single pulse respectively. The value of omega is related to the coding weight, indicating the probability that the symbol 1 appears in the n-bit bits data. Omega is usually set to 0.5. In order to make the probability of the symbol 1 and the symbol 0 the same. In a terahertz communication system based on TSOC modulation, the received energy consumption is usually set to 1/10 of the transmitted energy consumption 19. The energy consumption of transmitting unit bit data can be expressed as EBIT equals omega EPTX plus EPREX. 11. where E bit represents the energy consumed by a node in the transmission link P to transmit and receive unit bit data. If the node is a source node, which means the information the node senses needs to transmit to the control node, it is considered EPREX equals 0. If the node is a destination node, it is considered EPTX equals 0. The energy consumption for transmitting and receiving a single pulse EPTX and EPS are set according to the terahertz channel parameter setting based on TSOC modulation in 21. When the nano node's communication range is 2 mm, the values of the energy consumed by transmitting and receiving a single pulse in equation 11 are FIXED at 1 and 0.1. PJ. 3. Clustering Routing Framework 3.1. Network Layering. Layering the network helps nano nodes find the layers they belong to. Assuming that the monitoring area is circular, the entire network is divided into several virtual layers as the NC is set to be center. The width of each layer is R2, the radius of the LTH layer is L plus 1 R2, where L is the number of layers, and R is the communication range of each nanonode. This way of dividing layers ensures that the transmission range of each nanonode can cover its adjacent layers. When a broadcast message is received from the NC, all nanonodes calculate their distance from the NC, compare their distance to the layer radius, and register themselves to the appropriate layer. The algorithm of nanonode distribution over layers NDL is given in Algorithm 1. Algorithm 1. NDL algorithm. Notations. VK equals no of deployed nanosensors. DK equals distance of nanosensor VK with respect to NCL. VK equals layer number to which node VK is assigned. R equals transmission range of each nano node data. R, VK. Result. L, VK, NC broadcasts, hello packets, to all VK. For each VK to L, VK. Sensors 2019, 19, X for peer review. 7 of 23. Zeta, equals E, underscore, E, 13, where E, underscore, is the residual energy of nanonode VK, and E, is the maximum energy. If a given nanonode does not find another nanonode with a larger zeta, it declares itself to be the CH. After the CH is selected, clustering begins. The CH multicasts short-range messages that declare itself as the cluster head to all unclustered nanonodes within the same layer. Furthermore, each non-member nanonode compares multiple short-range messages it receives, sends a join request to the CH corresponding to the strongest RSSI received signal strength indication short-range message it receives and registers itself as a cluster member CM. This process continues until clusters are formed and all nodes have been assigned to their respective CHs. In order to reduce the clustering overhead, the entire network is only clustered once. After each round of data transmission, only the CHs are updated. The cluster formation algorithm, nano cluster formation, NCF, is shown in Algorithm 2. Algorithm 2 NCF algorithm. Notations. V equals no of deployed nanosensors zeta equals normalized residual energy of sensor versus K zeta equals nanosensor with maximum zeta GN equals general node data, L versus E underscore E. Result. Clusters for each versus. Do. Calculate zeta, with equation 13, multicast zeta, within associated, KLV. If K, zeta, then status. CH. Else status. GH. End-end elected CH multicast short-range advert message to GH within associated L versus. Semicolon. For each GH do check received RSSI from all CHs within range. Send join request to CHs CM for which RSSI is maximum and get registered. End. In order to prevent the cluster head node from dying due to frequent data forwarding, the cluster head node needs to be updated after each round of data transmission. An adaptive scoring function is used to select and update the cluster head in this paper. In the function, the distance from the node to the cluster head node and the remaining energy of each node are considered. The scoring function is a linear combination of residual energy and node position, and the node with the largest score becomes the cluster head. The scoring function is S equals WM E underscore E plus 1 minus WM times DN array summation minus D versus H versus DN array summation. Closing square bracket. 14. Where S is the score of node versus E underscore represents the residual energy of node versus, and E represents the maximum energy of node, assuming the initial energy of node is the maximum energy. H versus represents the cluster head node of node versus, dn area summation indicates the sum of the distances from all nodes in the cluster to the cluster head node, and d versus h versus is the distance from the node versus to the cluster head node. Wm is the weight coefficient. Fl or 2dk. R. Vk registers itself into layer L Vk. And the number of clusters of the LTH layer is pi. L plus 1 2. 2R2 minus LR2 2. B. R2 2 equals 2L plus 1. 12. 7 of 23. 3.2. Clustering and cluster head updating. After all nano nodes are assigned to their respective layers, the initial cluster head node is selected based on their remaining energy. In this selection process, FIRSTLY, the candidate nodes compete for the ability to become the cluster head CH by multicasting their weights to neighbor nodes of the same layer, and the nano nodes ignore the weights sent by their neighboring layer. In this process, the cluster head node reduces its transmit power to half of the original transmit power to ensure that the diameter of the formed cluster is less than r, thereby ensuring that the node can reach any other nodes in the cluster in one hop. The weight is represented by zeta k. Its calculation is as follows. Zeta k equals Arace underscore k. Emax 13, where Arace underscore k is the residual energy of nanonode Vk, and Emax is the maximum energy. If a given nanonode does not find another nanonode with a larger zeta k, it declares itself to be the CH. After the CH is selected, clustering begins. The CH multicasts short-range messages that declare itself as the cluster head to all unclustered nanonodes within the same layer. Furthermore, each non-member nanonode compares multiple short-range messages it receives, sends a join request to the CH corresponding to the strongest RSSI received signal strength indication short-range message it receives, and registers itself as a cluster member CM. This process continues until clusters are formed and all nodes have been assigned to their respective CHs. In order to reduce the clustering overhead, the entire network is only clustered once. After each round of data transmission, only the CHs are updated. The cluster formation algorithm, nano cluster formation, NCF, is shown in Algorithm 2. Algorithm 2 NCF algorithm. Notations. Vk equals no of deployed nanosensors, zeta k equals normalized residual energy of sensor Vk. K maxed zeta equals nanosensor with maximum zeta gn equals general node data. L Vk Arace underscore k, Emax result. Clusters for each Vk. Calculate zeta k with equation 13. Multicast zeta k within associated L Vk. If k maxed zeta, then status.
So next, we'll have Professor Michael Strano talking a little bit about engineering the nanoparticle corona for sensors at new biological interfaces. I don't think he's going to talk about it today, but recently he was appearing on Science Friday talking about some of his explosion detection technology. And I'll leave it at that. It's definitely online. It's appeared a lot in the press. So
good, good. Wonderful. Thank you very, very much. What I want to talk to you about today, I want to change gears and talk about a problem in the sensor space that no one wants to work on, and that's actually molecular recognition, generic strategies for molecular recognition. When we move from the cell phone into the chemical realm, if we want to sense chemicals in the body, we have very few methods to get selectivity. Nanotechnology is producing transducers that can get down to single molecule. I'll show you data now. We have sensor transducers that can basically count single molecules at room temperature in the environment. The question is, how do we make them selective? And that's the problem that is in need to be addressed. If you go into the clinic, you go into the hospital, most of the assays that are used to diagnose you come from Mother Nature. So the workhorse in general platforms for molecular recognition come from antibodies, and to a lesser extent aptamers or adaptive oligomers. Nature makes these molecules to be transient. So your body makes antibodies. They're designed to be broken down. But we use these and we expect them to function in the environment. We want them to last years. We want them to. So and these by far make up the lion's share of generic molecular recognition platforms. There is a technique called molecular in printing. It works some of the time. You basically polymerize a polymer around your analyte. It makes more of an adsorbent. But what I want to argue is that there's a pressing need for synthetic stable, non-biological molecular recognition sites. That's really the missing need in the sensor space. We have transducers that go down to single molecule now. So we've invented technology from my lab. We call it corona phase molecular recognition, or COFMOR, corona phase molecular recognition. And I can explain it. Many nanoparticles, you saw carbon nanotubes are featured heavily in the sensor space. There's a reason for that. Polymers like this amplifier will absorb around a carbon nanotube and solubilize it into a solution. So we call that absorbed layer a corona. So you're supposed to be seeing the rays of the sun. And the misconception in the colloidal community is that these corona phases are disordered like noodles. Okay, so noodles can't recognize anything. But if you do the following empirical experiment, if you make a library of these polymers and you make a library of corona phases, you do an experiment that actually shouldn't work. You can screen that library against an analyte library, and what you'll find is very exquisite cases of molecular recognition. And we call that corona phase molecular recognition. And it's very, very new. It's, we're using, in this case, I won't talk about the transducer. We're using a near-infrared fluorescent carbon nanotube. It's a nanoparticle. It fluoresces in the infrared. And we look for changes in its intensity and changes in the wavelength shift to indicate that a molecule has bound. And at this point, over the past 4 to 5 years, we have ample evidence that this can be extended to a wide variety of molecular species. But I'll give you a few examples. They really are surprising. So this molecule, which is very simple and unassuming, it's a polyethylene glycol connected to 2 hydrophobic fluorophores. This molecule sits on the carbon nanotube we know in this loop. We call this anchor loop corona phase. This polymer will recognize alpha and beta estradiol with exquisite selectivity. So we're not talking about an orthogonal dog nose type of interaction. It makes a molecular recognition site that's very selective. This is an analyte library, and you're seeing a relative fluorescence change. If I mutate this chemical structure to another anchor loop, you see the selectivity goes away, and it starts to look like just this lipid peg. This mechanism works at the nanometer scale. I'm sorry about the lighting here. You're supposed to see a carbon nanotube, and you're supposed to see the actual change in the corona phase at the single molecule level. You can see the deformation in the corona phase as a single estradiol molecule comes down and binds. I have a lot of examples of this. This is a corona phase that recognizes riboflavin. And again, it's exquisite selectivity. So it will recognize riboflavin, not other pendant diols, not FMN, things in your body that look like riboflavin. You get exquisite selectivity just for riboflavin. And it's from this polymer that a chemist otherwise would not be able to predict, that this polymer, when mapped to the carbon nanotube, gives you this molecular recognition. These probes have immediate biological utility. You can put nanoparticles into these are raw macrophages, and we're actually looking at, so these cells, this cell has our nanoparticle probes inside of it, and you're seeing in real time, spatially and temporally, riboflavin diffusing and changing its concentration throughout. So we've extended this method to carbohydrates, to proteins, to I'm going to give you some examples of analytical challenges that now we're solving. I had a postdoc, Sebastian Kraus. He was interested in neurotransmitters. There is no optical reversible sensor for dopamine until our work. And this gives you a sense of what a COFMOR screen looks like. So these are neurotransmitters that Sebastian screened against. This is a first-round COFMOR screen. These are different corona phases, different polymers that we've wrapped around the carbon nanotube. And the red is a fluorescence turn on, and the blue is a quenching. And you can see here that the corona phase strongly regulates which neurotransmitters bind to the surface. We found this really strong turn-on sensor for dopamine. It actually has some cross-reactivity with epinephrine, but actually it's the first optical reversible sensor for dopamine. It has wide utility. And you can see here, these are fluorescent carbon nanotubes dispersed on a surface. And if you add, let's see, sorry about here. If you add if you add one micromolar of dopamine, you see a very, very bright turn-on response, and you can do this. You can cycle this repeatedly. Each nanometer scale particle gives an independent, exquisitely sensitive sensor for dopamine, which you can show goes down to the single molecule. Basically, it has a single molecule detection limit, which I will show. So recently, in a paper that just came out earlier this year, we solved a major problem in dopamine detection in and around a neuron. So the only other way to detect dopamine directionally around a neuron is to use electrodes, and the record to date is 4 electrodes. If you put any more, you get cross-reactivity. So we have here, in this blue, we have 20,000 selective dopamine sensors that are optically addressable. We put a neuron on top, and this is actual data. If you stimulate the neuron with an action potential, this is happening in your brain right as we speak. If I haven't, so that if you take a look, what you see is it's not playing here. So that's good. Okay. Well, you'd see a very beautiful turn on response. I'm going to try this. Let me just try this. Try this again. Well, you'll have to come to our website. And you'll see what you'll see is that in the footprint of the cell, you see spatially and temporally the dopamine emission events in space and time with exquisite precision all around the outline of the cell. Okay, well, you can detect down to single molecules with many nanosensor transducers, but a fluorescent carbon nanotube is one. We've done a lot of work detecting nitric oxide. Here you're seeing single nitric oxide molecules binding from the bulk in real time. This is actually, or not in real time, but at room temperature in the environment. You can basically make a nanosensor transducer that can count individual molecules. We've solved the detection limit problem. There's no concentration below which the sensor doesn't work. So the question is making it selective. And we've made a nitric oxide sensor. Nitric oxide is a chemical signaling molecule used in your body, and it's very, very difficult to detect. So we were interested in this as a way of detecting these chemical signaling pathways in the body. And then I have a large part of my program is focused now on making sensor tattoos that operate in the body in vivo. So we're using Kaufmor to make fluorescent hydrogel sensors that can be placed in tissue. We're working on glucose. We're working on insulin. We also have a program on cortisol and progesterone. And the idea here is that you can use the near-infrared fluorescence of the sensor to monitor these analytes in real time using Kaufmor molecular recognition in these hydrogel beads that are easily put inside tissue. So we have a fairly extensive murine program. This is a paper that we wrote in 2014. We put our sensors for nitric oxide into A129 mice, and we actually showed operation of the sensor for more than 400 days. It's actually the longest any nanosensor to date has ever been demonstrated in vivo. And at this point, we have mice that spend their entire lives with these nanosensors in their peritoneal cavity or in the hind flank. We have very, very healthy diabetic mice. And so, but you can see here that this operates over for 400 days. So a remaining challenge that I'll talk to you about. So this is a paper also that just came out. So what's an analytical challenge? Could we detect single proteins coming from a single bacterium? Imagine that from a sea of bacteria. Could we detect the chemical emission from a single bacterium? That's an analytical challenge, and we recently published this in Nature Nanotechnology. This is work from Marquita Landry, who's now a professor at Berkeley. I can forgive her. She did not want to use Kaufmor. She wanted to use aptamers, which actually are very difficult to use. She did get partially an aptamer corona phase to work. What she showed is that if you have any hope of getting this aptamer, which can recognize an analyte, you need to use what's called an abasic spacer. So she wraps the nanotube in DNA. She puts this abasic spacer. You have to screen and find the right length, but if you do, you have a hope of getting your aptamer to work. So here she looked at HGH, HIV-V1. She could only really get an aptamer to recognize the analyte. Here's the aptamer on the nanotube. Here's the analyte. You're supposed to see here, she was only really able to get 2 bright turn-on responses for this HIV1 and this RAP1. The rest failed no matter what the basic spacer was. But these two make a very, very nice, for the cases that work, turn-on sensor. Whoops. And here she illustrates actually the advantage of a nanosensor that's selective. Yep, I've got. If you take a look, so if I take the sensor and I have it on a substrate, if I add up the signals from all of these sensor signals here, I get an analog response curve. And just like any other sensor, many of which you've seen today, there's a concentration below which you can't distinguish a signal from the noise. So there's a concentration detection limit in this mode. However, if you then look at just one, if you optically address just one nanosensor, you can actually count the stochastic fluctuations. Every molecule that absorbs and desorbs, you can actually count, and you can plot now the first passage arrival time. And this actually scales down. It goes down to single molecule. You don't get anything for free. It means that if you have to wait exponentially long, if there's a molecule in this room and you want to detect it, if you're willing to wait long enough, you will detect it. But it's still a significant advance compared to where we were 10 years ago. So this is what nanotechnology has given us. It's basically the ultimate detection limit. And so what Markita has done, she can see that you can look at a single bacterium, and these are E. coli, and they're emitting the RAP1 protein. You can see here in the red, you're seeing sensors lighting up from single proteins coming from that single bacterium. And so this is an exquisite detection limit that's demonstrated. And Markita went on to basically do some new biology. She showed that when the bacterium are dividing, they actually stop their protein production. They actually put their metabolism towards reproduction before they resume effluxing protein. And this is intuitive, but you can really only study this at the single organism level. And so that was. I'm going to leave you with an area of my lab where we've figured out how to get nanoparticles to traffic inside living plants. And so I have a new initiative in my lab where we're trying to use nanoparticles to transform living plants, giving them non-native functions. So can we replace the things we make out of circuit boards and stamp out of plastic with a living functional plant that has its own energy source, and it can be recycled, and it has lower cost. So here, relevant to today, I've turned really any wild type plant. We use spinach, but you can use any wild type plant. We've turned it into a chemical sensor by putting 2 nanoparticle sensors inside the leaves. We demonstrated that if you put explosives in the soil, they'll be taken up by the plant by transpiration. They'll activate two sensors of reference and an infrared, and we'll send that to your cell phone. So I have a quick, this is my last slide, and this video does work because we did check it out. Let's see, okay. And this is a spinach sensing plant. These are 2 nanoparticles placed in the mesophyll of the living plant. And we've done the detection with just a basic cell phone camera. This is picric acid being added to the soil. Within about 10 minutes, the plant will take up this water containing the analyte through the roots, through the stem, and into the mesophyll. We have a sensor that acts as an infrared reference, and this is just a Raspberry Pi system. It represents a very low cost. This is essentially the optics in your cell phone. And you see you have a reference, and you have a nanoparticle spot that modulates as the nitroaromatic is detected, and then it can send your plant can send you an email. So with that, I would like to thank my collaborators and thank the organizers of today's event. Thank you very much.
Michael, thank you.